Assalamu alaikum and hello everyone. My name is Muhammad Ridwan and we from Team 4 will be presenting on problem 3B. So referring back to problem 3A, here are a few guidelines that were given to solve problem 3B. And the main problem identification of the learning issue was to understand the feedback control system analysis. So now referring to problem 3B, we were told to test the stability of both loops and tune both feedback controllers, determine the stability range for the P controller tuning parameter, and to compare the controller in different control modes in MATLAB or Simulink to determine the suitable feedback controller modes. And finally, we had to finish a complete PNID via the control loops description, instrumentation info, and transfer function calculation. So the main learning issue for 3B, problem 3B, was the stability analysis of closed loop control system and PID controller tuning. So that is all from me. Thank you very much.
I'm Rohani from Team 4. For top column loop 1, the objective of feedback control loop is to control methanol composition in the distillate flow at desired level by manipulating the reflux flow. Control variable and measured variable is the same, that is methanol composition in distillate flow, and the disturbance is feed rate. The block diagram for this loop is like this. Starting from XD set point, we will go to sensor, and then error will be produced by the comparator to controller, and then from the controller we produce electrical signal to valve, and from the valve we produce reflux flow to the process transfer function, and then the output will be the changes of distillate methanol composition. From the disturbance transfer function, both of the output will produce a new distillate. At bottom column for loop 2, the control objective is to control methanol composition in the bottom flow at desired level for process stability by manipulating the reboiler deputy. The control variable and the measured variable are the same, that is methanol composition in the bottom flow and the disturbance in the feed rate. Based on PNID diagram, the block diagram is like this. Starting from measured variable XB, we go through sensor GM and then to the comparator. The comparator will compare XB set point and XB measured. To the comparator, error is produced and then sent to the controller and then sent to the valve by electrical signal, which produce new bottom flow rate and then go to process transfer function. And output will be the changes of bottom methanol composition. Feed will go to the disturbance. The output of the disturbance transfer function and the process transfer function will produce new bottom methanol composition.
I'm Xing from Team 4. Now we'll explain the transfer function in problem 3B. We have 5 transfer function, which is the GV, GC, GD, GM, and GP. So we let GC equals to KC since we use the P controller, GM equals to 1. So if KV is by using range of the molar flow rate divided by the range of the signal, we let GV equals to KV since both dynamic is negligible compared to the process dynamic. So we need to find the GP. Here, GP is the XD over R. So we use a step response from distillate composition and then the reflux rate. Now we have two conditions. Condition 1 is reflux rate is plus 5% change. We use the 2-point method to find the GP1. So we need to consider the delta and then also the differential to find the K, T63, T28 to find out the tau, and then also the theta we will sub into the equation, then get this one for GP1. And then GP2 is the condition 2 when reflux rate is negative 5% change. We use the same 2-point method. To get GP average, we use the data from GP1 plus GP2, then divide by 2, we can find the GP average. So to find out the disturbance transfer function is XD over F, use the step response from distillate composition and then the feed rate. Same goes as two conditions, plus 5% change for feed rate, and then negative 5% for feed rate, then we will get the GD average by using the 2-point method too. Then here is the summarize for the transfer function in loop 1. Then for the loop 2, GC equals to KC since it's using the P controller, GM also equals to 1. But KV here is different. We use the range of the deputy of reboiler divided by the signal change. So we will get 3030.30. Then we let GV equals to KV since valve dynamic is negligible compared to the process dynamic. So here GP is the XP over QR. So we use the set reference for the bottom composition and then reboiler deputy. So we also have cool condition plus 5% change in reboiler deputy and then negative 5% change in reboiler deputy. So we get a GP average. And then for the disturbance transfer function is the XB over F is the bottom composition and then also the feed rate step response. And then here also have two conditions plus 5% change, negative 5% change, so we will get the GD average by using the 2-point method too. Here is the summarize for the transfer function in the loop 2. For the stability analysis, we have two criterion. First is general stability criterion, second is route stability criterion. So in loop 1, we consider the general stability criterion first. We will have characteristic equation 1 plus GP, GV, GM, GC. So we'll sub GP, GV, GM, GC into here. Then this one exponential, we can change to this one by using 1 over 1 back approximation. Then we'll rearrange the equation until here like this. So we'll consider 4 conditions. Let s equals to 0, calculate the CASI. Let s equals to 0.1, calculate the CASI. Let s equals to negative 0.1, calculate the CASI. Let s equals to negative 0.2, calculate the CASI. But remember, here, the conclusion, we need to consider s smaller than 0. So we will find the stability range for CASI is greater than negative 253.872. For the second one is route stability criterion. Here is called the route array. How we rearrange the data from the equation into route array will based on this form here, like this. Then we can using this formula to find out the stability range for the CASI. So we will find out the range for the CASI. So for the loop 2, we also use the general stability criterion, then sub GV, GP, GM, and GC into the equation. Then using 1 over 1 back approximation, change the exponential function, then find out the range for the CASI. Same goes to the route stability criterion too, so we'll get the range for the CASI.
Hello everyone, I'm Sabrina Yong, so I'm going to present on the tuning method. So moving on to the loop 1, which is the top column, by using the tuning method of offline Cohen-Coon method. First, we have to calculate the GPRC, which is equal to GP and average GMGV. The value of this GP, GM, and GV can be obtained from the previous slide discussed by Xin Yi. So after substituting the value into this equation, we obtain this, multiply everything, and we will obtain this. So GPRC can also be represented by this formula as well. So by comparing both of these, we will obtain the K value, which is equal to 0.003939, the tau value equals to 61.5, the data value equals to 5.5. Moving on to the P controller, by using the Cohen-Coon tuning formula, substituting the value from the previous slide into this equation, we will obtain this value, and this value will actually be substituted inside the P controller simulink. So as you can see, the setup for the simulink, we have the P controller, the controller gain, the transfer function to show how the WAF respond, GB, the transfer function to show how the process respond, GP, the delay, and the GD disturbance, and this is the GM. This is also the scope to look at the response. So after running the simulink, we will obtain this response. So for the PI, same thing as well, by applying the Cohen-Coon tuning formula, by substituting the equation of KC and tau1, we will obtain this value, and running the simulink, we will obtain this process response. So for the PID, same thing, substitute the KC equation formula, tau1 formula, tau2 formula, and we will get this value. And running the simulink, we will obtain this response. Moving on to the online Ziegler-Nichols method, by using a try and error method, we have obtained the KCU is 3612 and the PV is 35.06. So by substituting KCU and PV into the equation, we will obtain this table of value. So this table of value, we will substitute the KC value, tau1 value, and tau-d value into the simulink, the P controller, PI controller, PID controller, and we will obtain the response. After running the simulink, for the P controller, the response will be this, and the response for PI controller is this, and the response for PID controller is this. Moving on to loop 2, which is the bottom column, using the offline Cohen-Coon method. First, we have to find the GPRC by using the formula, substituting everything inside, and we will obtain this. This value can also be obtained by previous slide discussed by Singyi on loop 2. And substituting the transfer function into this equation, we obtain this, multiply everything, we obtain this, compare of GPRC with this, and we obtain K, tau, and theta. Moving on to the P controller, by applying the Cohen-Coon tuning formula, we will obtain this value, and running the simulink, we will obtain the process response. So it's the same, the only difference is, it's the same as loop 1, but the only difference is the GD, GV, and GP is different. This is the transfer function for loop 2. Okay, moving on. For the PI controller, similar as well, substituting everything inside, and we obtain the value, running the simulink, and we will obtain the response of the process. And after that, for the PID controller, same thing as well, substituting the value into the KC formula, tau1 formula, tau-d formula, we obtain this value. This value substitute into the PID controller in the simulink, and we will run the simulink, and we will obtain this response. Moving on to the online Ziegler-Nichols method for loop 2. By using trial and error, we have obtained the KCU equals to 266.50 and the PV equals to 39.8. And after substitute KCU and PV value into this equation in the table, we obtain this table of value. And after substituting the value into the controller in the Simulink, we will obtain and run the Simulink, we will obtain the response for the P controller, PI controller, and PID controller. And that's all from us. Thank you.